Good afternoon, everyone. My name is Desmond Martin. I'm the Chief Learning Officer at NextWave STEM, and it is my very good pleasure to have you join us this afternoon for teaching drone coding using project-based learning. This is actually going to be a really exciting topic that we get to jump into today, especially with the new school year coming up. Something that we've been dedicated to more and more at NextWave STEM is really expanding into new, interesting, and engaging emerging technologies. And the context of the last school year, really what we've seen where many of us, if not all of us, have had to make dramatic adjustments to the way that we teach, has prompted us to think about ways in which we can make project-based learning work for students, regardless of whether they're in the classroom or if they're away from the classroom, regardless of whether they have access to the physical drone, or we have to be a little bit more creative with what our students can learn about the emerging technologies. We're going to get a chance to talk about what project-based learning can do for us in the context of drone learning today. Very excited for the topic. Before we get started, however, I do want to cover just a couple of ground rules. The first is that we are in webinar mode today. That means that we won't be able to hear you and we won't be able to see your face. That's not a problem though with regards to communicating. We have some of our participants who have already joined us. The chat is open. That means that if you have any questions or any comments or just would like a little bit more information, you can drop a comment in the chat. I'll see it live during the course of the webinar today, and we'll get your comment or your question addressed live on air. The second thing that we want to cover is just what you'll be getting as a takeaway from the webinar today. Because you're here joining us live, you'll be getting a copy of the slide deck from today's webinar, as well as your certificate of attendance. For our teachers who are here located in our home state of Illinois, today is a PD credit hour. You'll be able to turn in your certificate of attendance to ISB and make sure that you get credit for your attendance today. For those of you who would just like a token of your time with us, you will also be getting that certificate of attendance as well. Be on the lookout for those documents after the webinar today. And for your colleagues who might not have been able to make it but are very interested or might be interested, feel free to share the recording of today's webinar. We're going to be recording today's session. We'll be pushing that out in the email following today's webinar as well. If you know someone who it could be useful for, don't hesitate to share the good word. With that being said, we will go ahead and press forward and begin with just a little bit more about who we are at NextWave STEM. NextWave STEM is a young and aggressive STEM startup company. We are just now entering into our 4th year. At NextWave STEM, we believe that students are going to be critical, and the students of today specifically are going to be critical to solving some of the world's most challenging and most difficult issues. Climate refugees here in the United States are a real thing right now. We're dealing with issues of food security. We're thinking about what the future of employment will be in a world that's rapidly globalizing, but also rapidly automating. We have to empower our students with those skills to allow them to adapt to a world that they may not be able to predict. And some circumstances that they definitely won't see coming. And as we do that, we recognize that it's you as educators who are the most critical portion of that equation. In order for our students to be adaptable and actually have some skills that translate into this really uncertain world that they live in, they need teachers that can teach them. They need teachers that can teach them concepts in science and how to use technology and how to solve problems like an engineer and advanced mathematics. We need those skills in our students, but in order to have those skills in our students, we have to first have those skills in our teachers. So at NextWave STEM, we really believe in supporting you as an educator, making sure that you've got access to the material to teach STEM, and especially STEM with emerging technologies with a high degree of confidence and fidelity. What does that mean? That means that we provide courses in emerging technologies right now on 3 particular technology tracks that are NGSS aligned and support grade band learning towards 21st century skills. We'd like to think of ourselves as an all-stop shop so that you can have what you need for a really successful, really engaging STEM program. We'll talk a little bit more about those materials a little bit later on in the webinar. And we are really, really happy to connect you with our school partnership manager if you'd like to know more. But today we want to focus on really specifically two goals. We want to define the questions and challenges that drones are able to solve at home. This is the idea that our project-based learning is really longitudinal. As our students are working and developing skills, a lot of those things that they've had to do traditionally in the classroom have migrated onto digital learning in the course of the next 15 months. And we live in a world where we know that our students may need to adapt to these newly acquired skills and continue to build these skills over time. That's going to be really critical for their work in this currently and continuously evolving 21st century. That means learning some things at school, out of school time, and as well as in class, but also doing work from home. Look for the ways that drones can help us with that. But then the second thing that we want to explore is the place of project-based computer science, or block-based, I should say, computer science in project-based learning. A big barrier for access to emerging technologies is actually a prerequisite computer science knowledge to be able to really engage with some of the really robust technology students might want to work with. If you're not a full stack web developer, if you're not a guru and you can't code Python perfectly, a lot of technologies may be close to you. But as we continue to learn and grow in our understanding of the importance of computer science education, that means a lot of our technology and our physical hardware is catching up with where our students are, that there's lots more options for access for students who might not have very much experience. And this is doubly true for us as educators who might not have a whole lot of computer science experience. We're creating a paradigm in which our students can also participate. Really interesting to see what those variable options look like for us. So we'll go ahead and we'll dig right in, exploring the idea of what project-based learning is and what it is not. Many of us have worked in some kind of project-based learning modality or even problem-based learning modality, but we want to explore with a little bit of depth the difference between what we might traditionally do in our education curricula, but also what project-based learning offers us. So it's useful oftentimes to begin with the definition when we want to explore this idea of project-based learning. The Buck Institute of Education, specifically their PBL Work division, is an awesome research to explore project-based learning in a lot more detail. And they define project-based learning this way: that project-based learning is a teaching method in which students gain knowledge and skills by working for an extended period of time to investigate and respond to an authentic, engaging, and complex question, problem, or challenge. That is an awesome opportunity that we've been presented in the form of really making this learning real for our students. First, by exploring the ways in which technologies serve problems today and could serve problems in the future, but also because we're really not roped into this idea of being locked into time. Yes, we still need to assess. Yes, we want to make sure we cover a plethora of ideas and concepts as we're working in computer science specifically, but learning about drones as well. We want to make sure that we're covering some really useful requisite knowledge, but project-based learning more than anything is longitudinal. Your project-based learning experience can last weeks or months on end. And because of the diversity of student work available, that means that we can dig in and do some really interesting, really different things than what we might think is just relegated to our STEM class. When we consider a history of project-based learning, what we're thinking about is actually a continual progression of human teaching pedagogy throughout recorded history. You can go back as early as ancient Greece and ancient Italy, to philosophers who were advocated the idea of learning by doing, not just rote lecture, but actually going and trying and doing things, to pioneers like Maria Montessori, who really focused on student-driven and student-led experiences, students choosing their pathways, and we as instructors creating these opportunities for predictable risks and predictable failures and this really interesting and engaged way of learning. It becomes critical that our students have to do in order to be effective learners. So when we focus on project-based learning, what we're thinking about is a particular instructional model that moves our students through some key moments, some key steps. The first is this idea of exploring a driving question. And this goes back to the overarching thought process that our students need to be doing work that's authentic, that engages the real world and engages real world problems. Choosing a driving question becomes a critical step in that process. But once we've chosen that driving question, not just something that we find interesting, but that's something that affects real people and even affects us in our communities. Once we've done that very important step, we move into the space of inquiry and research. A lot of our student-driven work is going to be about what don't we know and what do we need to learn more about. If I'm solving a problem or if I'm engaged with a project that impacts really real people, it becomes imperative that we actually have conversations with those real people. That's part of the question asking and the research that we always want to encourage our young learners to do. Once we've gone through this process of being really curious and doing research on our subject, we move into this amazing space of student choice. That's another really defining characteristic of project-based learning. The fact that we're not so much driving the car with respect to the kinds of work our students are doing. What we prepare for them are multiplicity of different paths and different work that they can do to solve their problem, or accomplish their project. So we're creating these scenarios in which our students' final work, those things that they're evaluated on via various rubrics, can look really, really different from work that other students are doing. And we have these really individual, really gratifying assessment moments that will continue to rise through the course of the project. Once our students have made some choices, there's the idea of project design and feedback. We as instructors during that feedback moment, that continuous positive feedback loop as we're assessing our students working through their work, we'll actually have the opportunity to not necessarily choose for our students, but guide and steer our students into some better choices, into some more diverse choices for their learning. This all comes down to what our goal is for this particular project. After that, there's this presentation, this grand moment where our students' final work product is not only for them, and it's not only for you as an instructor for the purposes of evaluation or assessment. That becomes the actual engagement with the community, the actual engagement with the end product user. If we're solving a project for a real person, then it makes sense for us to consider how the solution will actually impact that person. To have that be presented to a principal or to a school board or to the community group or to a parents group. We want to make this as real and engaging as we can. And from there, we move into our reflection moment, where students are actually able to process all this work that they've done. We can see just in the setup, just in this definition of a learning model, that we have the opportunity to really change the paradigm with which our students approach, not just learning generally, but learning about emerging technologies specifically. Our students should expect for this work to be for the long haul and just not a side dish or a dessert option with respect to their STEM education. And we can kind of think of this and contrast that in the difference in the way that we think about a traditional learning unit. That we will launch a unit and have this loop of lesson and then activity, teaching the actual lecture side, and then some kind of accessible worksheet or performance task, the assessment, back and forth until we get to a capstone project. This is not the way we want to think about our learning. Instead, we want to create this continuum of work that allows different options, kind of what we talked about before. So we begin with our project launch. That's our driving question, and automatically we're into different categories of student work, whether that's working through activities or lectures or homework or research, moving into a benchmark moment where the rubrics we've established for the different types of work we've done become assessment moments. If it's doing a research paper or if it's conducting an interview, we have our different rubrics and tools to help us assess those moments. If it is conducting a book report or citing sources in research, we have different rubrics that assess that. That puts in place the idea that our students are able to explore exactly what they want to explore and why they want to explore it. But also, once we move past the benchmarking into that reflection moment, we now have this awesome opportunity to turn around and say, perhaps your research was really, really good. Let's move you now into the space where we want you learning some particular skills. That may be reading, that may be doing, that may be actually working through some skills and challenges through programming, that might be in dialogue with an expert. So we're going to move you to the next thing. It really comes down to what we're trying to accomplish with our course. And we can have these benchmark reactions and student work loops happening over and over again until we get to this point where we're at our final event. We're making that presentation and we're ready for the reflection. We're building our students' investigative practices even as they're investigating the next step of work that they might do. So a great place to begin, especially when we think about emerging technology, is this driving question. Whether we're doing this work in the context of our schools during school time, whether we're doing this work in the context of out of school time, in an after school program or in a summer learning context, whether we're doing this work in the context of during school time, but remotely, something that many of us have been doing for a while, and for some of our student populations is still very much the work that they'll be doing for the foreseeable future, is finding curricula and being able to differentiate in such a way in which we're not leaving anybody out, we're not leaving anybody behind. The ability to choose a driving question that's relevant for your students regardless of their learning context, whether that's remote, in person, or hybrid, or even a combination thereof. That driving question will also speak to those particular circumstances. That's another layer of assessment that we have to consider for our students, but also because of the technology that we're using, because of the focus of drones for emerging technology, we have some awesome opportunities for students to make this technology real in their particular context. What does that mean? Well, the first thing we have to understand is that as we are deciding about ways that drones can be used at home, we have to consider the way our students use technology at home generally. Students and educators, you're working together in this context. And a lot of this information we already know, but a lot of this will just come from your students' own personal observations about the ways in which they use technology. Key questions here are going to be around things that your students do and things that can be made better. In fact, in engaging that key question, we're engaging and activating in our students the ability to explore the engineering design process, just considering an end user's needs. So as you're working together, as you're defining that driving question, whether that question is in the context of school or if it's at home, whether that's using any kind of technology, there are some things we want to consider. The first is, of course, what's the problem that currently exists? What's something that makes your life a little bit more difficult? What causes some kinds of conflict? What's something that could just smooth things out for you or someone around you? What's a complaint that you've heard in the context of your home from a parent, from a sibling, from another co-member, from a community member, might be your neighbor? What's a problem that currently exists? The second question is, what are the tools available for me to solve that problem? If the problem stated requires a particular kind of resource, I might not have those tools available. But if I have the resources of an emerging technology, say a drone, we might be able to explore some solutions based on the context of your problem. And then finally, this quality control question. What can I do? How can I ensure that those who the problem is being solved for are actually receiving a real, I'll call it in this case, a viable solution? One thing that we understand from the engineering discipline is that as we're solving problems, as we're applying science, technology, and mathematics to solve problems for people, we may be creating problems for others. If I'm working on land irrigation, and that means I'm diverting water from a source, what happens to that area where the water was diverted from? If I'm solving a problem with regards to transportation and making it easier for people to travel from their home to places of business and places of recreation, what does that infrastructure do to the landscape? What does it do for the amount of time that we spend in commutes? Even if we think about our own technological solutions, if I'm creating a tool that's really easier for my students to use digitally, something like Zoom, what does that change about my students' expectations for how they will learn? We're fortunate that the pandemic has forced us to explore some of these questions, even from a really longitudinal perspective, heading into month 16, many of us being removed from physical contact and physical instruction with our students. But we know if we have students who have been in the classroom with us for a significant amount of time now, that our student expectations have changed, that our community understandings of what happens in our classroom has been adjusted, and that we've had to help move our students back into this space. How do we make sure that the things that we're working on are actually beneficial as these different modalities for learning have changed? We have to really consider that, not only amongst ourselves as educators, but alongside of our students. So there are a couple of different contexts in which we can explore real world driving problems. And these are ripped necessarily from the real world. Two companies, both of them are actually owned by Amazon at this point. If I wanted to contextualize this for my students, something that they might think about, one, using a drone, we can think about the security context. And I encourage us all to really take time to kind of brainstorm and think about the ways emerging technologies are being applied to their own personal context, but what they may have seen from outside resources, from the news, even from ideas of science fiction, become science fiction, become science fact, oftentimes if applied with enough time. We're seeing more and more drones being used for security and public safety purposes, both in interior spaces like we see in the context of the Ring drone, or even in exterior applications. And this becomes a really, really important context when we think about vulnerable populations, those who need the extra protection of security systems that can be adaptable to non-specific environments. How can we keep people safe? Drones can help us with that potentially. But another idea that's much more prevalent and becoming more and more relevant in the context of logistics and delivery. In a world, especially in the United States, where our infrastructure is becoming more and more crowded and more choked with automobiles. And much of that infrastructure needs to continuously be improved and rebuilt. We're seeing drones become much more important way to both deliver and send goods from one place to another. In this context, we can even imagine drones delivering goods to places that are much more remote, places where there is very little to even no infrastructure available. It's all about protecting and serving disconnected and vulnerable communities. We have, in this case, two examples. One that's really intimate and interior, and one that's much larger and has the potential to cover a lot more area. But the cool thing, the really cool thing about exploring emerging technologies is that because we're fusing the physical and the digital, we're now creating this context in which our students may be able to explore both. Not only because they might have access to the drone, but because we can do some things virtually that we can then extrapolate to that drone hardware later on. So the really, really important thing to take away from this idea of expanding and choosing a driving question that makes sense, whether that's an example of coding and flying a drone for security purposes in one example, or flying a drone with the purposes of actually delivering packages in another example, of understanding the underlying computer science that makes that work. That in and of itself, and in a lot of circumstances and situations, might be cause for the project-based learning experience, just that in and of itself. However, we can just imply or apply the tools that are really useful for us to actually simulate drone flight in the real world. And we can do that, once again, not by doing really hard, really robust, really difficult syntax specific computer science. We can do that using Scratch, drag and drop coding, something that allows for powerful ways in which our students can understand processes in computer science without necessarily learning a whole new language from the ground up. So what I'm going to show you here is an example of that idea in action. Learning computer science that is really applicable, but not having to learn a complete new language and syntax from the ground up in order to see our emerging technology in action. At NextWaveSTEM, our drones courses, 3, 5, 6, 8 in high school, are employing a particular technology called drone blocks. We love drone blocks at NextWaveSTEM, one, because it creates a really accessible way in which our students are able to fly drones, whether they're flying as individuals or in groups. But we also love it because it gives us this ability to explore autonomous flight, actually programming our drone to fly, pushing a button, and then watching our drone go off and accomplish a task. This is the next paradigm with which actual work with the drones is going to happen. And this is the natural progression of technology that we should expect to see over time, that drones are doing work as an applied technology to make our lives a little easier, to free up our hands, to free up our minds, and to give us the ability to do some other more creative tasks. In drone blocks, you can see that we really have two major areas with which to explore. The first is a simulation space. In the simulation space, if I zoom in very closely, we can see a virtual representation of a drone. And this virtual representation of a drone represents a real world drone that your students will connect and fly. It's the exact same model that will be following the exact same computer science. So we'll be able to see in this virtual space what your drone will do in the real world becomes a critical component. But even more critical for what's going to happen is what will happen in the computer science space, in the independent coding environment, the IDE. On the left-hand side of our screen, we see a plethora of different block categories. And if I click on one, in this case, the navigation category, we actually see bits and snippets of instructions that our computer, and the computer in this case being the drone, will be able to follow. Block-based coding, Scratch coding in this case, and variations of Scratch coding allow us to drag and drop specific instructions and sequence them in such a way that our machines, in this case our drones, are able to do exactly what we need them to do. For example, let's say I want my drone to take off, and after it takes off, I want it to fly forward. But I don't want it to fly forward any random amount. I would love if my drone was flying forward a specific amount. In this case, I'm going to make it fly forward 300 centimeters. Now, many of you might be asking, hey, Desmond, why'd you change this measurement? Why'd you change from inches to centimeters? What's going on in this context? We are in the United States of America, based here in Chicago, Illinois. All of our schools that we work with have been American schools from coast to coast, whether that's in Chicago or California or in New York. But the question here becomes, okay, what's the change from these imperial units now to metric units? One, we want to continue to develop the scientific reasoning and understanding within our students. It's really a lot easier to do that using the metric system, the accepted standards with respect to scientific inquiry. But two, when we're flying our drones in the real world and we're flying them autonomously, it makes a little bit of sense for us to fly in the context, especially if we're going to be working indoors or at home, flying in the context of smaller units that we can control and be ready for. So I can set up my drone with a basic instruction. Scratch allows me to drag and drop and connect different pieces of instructions in order for us to make the drone do exactly what we want it to do. Let's start with a basic one. We'll tell the drone to fly forward. And after it flies forward, I'd love for that drone to fly to the left. I'm going to have it go a little bit shorter this time. We'll have it fly 200, and we'll make sure to go from inches to centimeters, of course. And that's good for a start, just to get a sense of the drone's movement as it flies in our virtual space. After it's done that, we'll love to save a little bit of battery, so we'll tell our drone to land. What you just seen me do is write a program. I've constructed the computer program in 3 clicks, dragging in 3 instructions. There are 4 instructions in total. And the amazing thing is that I only needed to touch my keyboard to change any of the instructions when it came to changing distances. That was it. I don't have to worry about semicolons. I don't have to worry about dashes or hashes. I don't have to make sure that my brackets were closed. When I try to run my program, there isn't going to be some kind of error message saying that I didn't put a comma someplace or that I misspelled something. Instead, we've created a set of instructions that the machine can follow, and we've done that just by dragging and dropping. And doing it that way opens up a vast world of possibility for our students who may have never experienced computer science before. This is a critical idea at NextWaveSTEM. It sits at the heart of what we do and what we develop, that no matter where your students are on their educational pathways, no matter your prior experience as an instructor, we're providing material that you can jump into and implement with your students in a really robust way. So with that being said, I can actually zoom on out and we can open up our menu and launch the menu, launch the mission, and we'll see our drone take off and fly. Our simulator actually shows our drone take off in the air. You can see in our independent coding environment that we have the blocks of code highlighted, showing us what the drone is doing in real time. We can even rotate around this 3D environment and see our drone here. That is a really, really simple, easy simulation for the way that drones could move through the air. And the important thing to recognize here is just as this drone moves through the air in a simulated fashion, if I were to take the same code and connect my computer to my drone in the real world, my drone is going to do the exact same thing. What we've done is allow our students to explore the digital environment first and then explore the physical environment of the real world through the actual physical drone. Mind-blowing ideas, especially with respect to a technology that can seem a little bit intimidating at first for our students and for us as educators. And while this looks really, really simple, okay, the drone took off and flew forward and turned to the left and then landed, because we're working with a drone, because this is an emerging technology, because of the nature of what a drone is, a flying device, a flying craft, we're able to create a context in which our drones can do extremely complex maneuvers. As simple as focusing on the navigation, of course, we can move in our 6 cardinal directions, up, down, left and right, forward and backward. But we have the ability to fly in diagonals using the 3D Cartesian coordinate plane. For our students who are in 7th and 8th and beyond studying advanced geometry, even trigonometry, we can have our drones fly in particular curves around this three-dimensional plane. We can fly in sine waves. We can fly with respect to the pi ratio if you wanted to make our drone hover or circle in a particular way. And all of this is happening with drag and drop code. But not only are we controlling how the drone moves, but we're controlling, really, really important, the actual instructions that the drone follows. If we jump down into our loop category, we can tell our drone to repeat a certain set of instructions a certain amount of time. Well, if we focus on logic, we can do things like conditional coding to say that if one condition is true or if a condition is not true, that different sets of instructions might be followed. We can do complex mathematical equations. Things like, of course, being able to do simple arithmetic, but not only arithmetic, but also exponential mathematics. And on top of that, we can work with inequalities, take specific calculations, things like square roots or absolute values. And as I mentioned before, there are even constants that we can work with, things like pi or theta or the square root of 2, as we're considering how the drone will move through the air. If we want to expand upon our students' algebraic thinking, we can define and insert variables, calling a variable anything I want to, something like length. And we can set length to be even a particular number. And then using drag and drop coding, insert that variable any place we want to into our code. The ways in which we can expand from the beginning of really rudimentary elementary mathematics up to and including high school trigonometry and geometry is really, really, really exciting to think about considering flying drones. Oh, we got a really good question here from Mali. Sorry if I'm mispronouncing your name, my apologies. Nali asked, but why would you need to use the square root, etc., with a drone? Really, really great question. That comes into the idea of changing the ways in which drones will fly. A good way to think about using a square root function or using a constant like pi is if I'm coding conditionally and I want to program in my drone to make really specific and even slight movements. For example, if I were to program my drone to fly forward, and then I wanted my drone to start to make some movements. Let's say I want my drone to fly in a diagonal. And in this case, I'm going to use the variable as my friend here. I'm going to pull this variable out and set it off to the side for now. What I can do is use a square root function. And as I'm constructing my code, I can create an example for what exactly I want this code to do. Instead of calling this variable length, I'm going to, well, yeah, we're going to leave that alone. I'll leave the variable as it is. We can consider this variable to be like any variable that we would use algebraically, just something that we can change easily over time. And that can stand for any value that I want to give it. So the square root function becomes a useful way for us to consider ways to decrease a distance over the case or the course of an entire program. Let's say, for example, and I'll use a little bit of logic as well. So we'll do a loop. This will make sense in just one moment. And let's say, I'm gonna grab another idea here, which is a change. So I've just created something a little bit more complicated, but there's this basic idea here in which we are actually giving our drone some specific instructions. The idea, and you can kind of read it out in what we've built, is that we defined a variable for our drone, and we've defined that variable as a length. Now, in the repeat in this case, I'm telling my drone to fly forward a certain distance, 300 centimeters, and I'm going to make it fly in a diagonal. Those instructions are not so important to the idea of the square root. However, when I get to this idea of length, if I want to drastically and exponentially decrease that length that it's from, and in this case, I'll actually sub in length here. What I've created is a pattern of a drone, and we'll fly an example. So I'm actually going to change length to something a little bit more reasonable. 100. Launch this mission, and we'll be able to talk it out. In fact, there's a few more changes I want to make to the code here. Really good question, having me program off the top of my head. And we'll launch the mission. What we can do is use that square root to decrease the value really, really quickly. Our drone is in the air, and if we define an initial value for how far our drone should fly, what we can then do is decrease that value really, really quickly. I actually did not, there we go. So I actually have something kind of strange here happen in the code. Let's try that again. You can imagine our drone flying a distance far and then decreasing that distance exponentially really, really quickly by a root of 2. Say in a search environment or search scenario. If I wanted to autonomously have my drone navigate to an area and then search in really, really small increments using my camera, taking that length that the drone is flying or taking the distance that the drone is flying and using a root to make that value really, really small becomes a really, really useful and integral way to fly the drone. That's a really rough example of taking a value and making it really small. But the reason why we would use a square root in a variable there as opposed to plugging in specific numbers is that we can then have our drone be more responsive to a real life situation. If I don't know exactly how far that distance is, or I'm making my guess that's estimation, I don't want to go in and be manually changing all my numbers. Instead, I want to create the most efficient and effective way of getting that smaller number really, really quickly. An exponent like a square root would be a really easy way to do that. We can even think about that if we're doing decreasing values, even thinking of something like a Fibonacci sequence, where we want to make the scale in which our drone is moving or flying smaller and smaller and smaller over time. That's a really, really good question there with respect to drone flying. And using that particular square root function. You can explore some more in the Drone Blocks curriculum. Drone Blocks is one of our trusted partners here at NextWaveSTEM. If you are purchasing courses with NextWaveSTEM, you have access to all of their curricular content as well. We just want to make sure that you have the opportunity to explore some more ideas inside of Drone Blocks. Really good question there. So the idea here with Scratch is it allows us to do a couple things. So it allows us to program at a very, very wide spectrum of mathematical understanding without having to have a super, super duper robust understanding of how to program and code, because the work that we're doing is block-based, drag and drop. Your students have iPads, they're able to do this work just by tapping with their fingers. If your students have their computers, they're able to do this work typing on their keyboards and clicking with their mouses. And it translates directly over into their physical drone. So if we know we have some tools available to us, one tool that enables us to simulate, and another tool that allows us to connect to a physical drone and actually put the drone in the air, see the drone flying, where exactly might the student work go from here? Student work going from this portion is really based upon the scenario and particular situations that you're working with. If you're in person and able to connect with your students and connect them to experts and even your own equipment, a lot of this is going to be in the same classroom sessions, coding your drone and simulating a flight, moving that code directly over to a drone and testing and flying your drone for that simulated solution right in the midst of the flight. That's a really, really important and critical idea, is that things go from being virtual to being real, being in the real world space that becomes available for your students right away. Now, another idea that becomes really important once we go back to simulations is the ability to model. For our students who may be working specifically at home, we can translate even the flight that we're doing in simulated space by making that drone technology available into the space of their home by scaling. The simulated flight allows for the drone to fly in virtual space. A scale flight allows us to just take that real world flight that we might do around our school or in our community and literally cut it down to fractions of the size to be executed around the home or outside of the immediate home. That means that something like a backyard can become our drone testing space using the same problem solving skills and methodologies, just at a much smaller scale as our students are actually engaging this. Student-led work with the drone lives in the digital space, but also in the physical space. For engaging PBL with the drones, the only difference might actually be scale and your particular supervision as an instructor. So that's a lot of information, a lot of ideas with respect to how drones can help with project-based learning, from choosing a driving question that's relevant for your students and relevant to the topic, but also drive a really intense amount of mathematical learning and also bolstering our students' understanding in math. We also see with drones how we can engage spot-based coding to build that CS skill set. And that can really happen for any age of our students and become useful for us as instructors as well. That is great. But we want to think about other things that NextWaveSTEM can do to help you in your specific needs here in Chicagoland and beyond. I know I mentioned a little bit earlier in our webinar that NextWaveSTEM, we do so much more than just work with drones. It's one of our favorite things that we do, but we have K through 12 courses in 3 particular emerging technology areas: in robotics and artificial intelligence, drones with coding, and with 3D technology. Our courses really prepared your students to work with emerging technologies that they may not have worked with before. If your students have familiarity with the robotics, they may not have had practice actually building and coding the robot. That's something we do at NextWaveSTEM. If your students have never flown a drone before, they'll fly the drone both manually and autonomously while they're trying to solve real world problems. If your students have never done any kind of 3D printing before, they'll learn how to design for 3D, how to actually program your 3D printer to print and then generate a 3D print. We want these courses more than anything to be hands-on and engaging for your students as they're learning more about these techs. What's really also important to us at NextWaveSTEM is making sure that the curricula is challenging and age appropriate for your students as they engage. The K through 2 courses through the 9 through 12 courses is built taxonomically as your students acquire skills and knowledge. With respect to the K through 2 courses, it's a basic understanding of what the technology does. In the 3 through 5, we begin to understand the real world applications of our tech. In the 6 through 8 courses, we're evaluating this tech in the impacts that they have in the real world, starting to make some legitimate value statements and judgments based on what we're learning about the technology. And in the 9 through 12 courses, we're actually solving problems. Once again, in NextWave STEM, we really do focus and strive very hard to be a place to have a turnkey solution, a one-stop shop. That means you'll have access to our course material and equipment, but also professional development and training support. Because this is a new paradigm for so many of our learners and us as instructors being lifelong learners, it's important to make sure that you have access to the training and ongoing support that you need. And we're able to customize professional development, extra equipment, and certificates of completion for you and your students as you engage with NextWave STEM content. But we also at NextWave STEM really focus on providing a solution for your students if they're still working in the hybrid scenario. In the Chicagoland area, we have a group of trained, certified instructors who can come into your during school or out of school time class and deliver NextWave STEM content. And they're practiced and fluent in the technologies, but at distance. If you're joining us from outside of the immediate Chicagoland area, we can conduct your courses via video conference with your students, using the technology as well to make sure that you have the actual experience that you'll need. And that remote and in-person flexibility is really critical going forward. NextWave STEM material is designed to be used both in person and or remotely. You want to make sure you have a solution that will work best for you. So I know that was a large amount of information in a relatively short amount of time. There may be questions bubbling up. We had a really good question about the actual drones and how we could apply a specific mathematical function to control their flight. And those are the kind of in-the-weeds questions that I love. Are there other questions that anyone has about flying drones in the context of a PBL or anything else that we've covered here today? This is the moment where I'm quiet and I let those fingers go flying across your keyboard. I'm not seeing any other questions pop up in the chat or in the Q&A functionality, and that is just fine, not a worry at all. You may be ruminating over some of what you've seen today and want to come back with a question a little bit later on. And if you have any questions, my email address is really easy. You can reach me, if I can avoid some stutters in my slide deck. You can reach me at desmond@nextwavestem.com. I am really good about connecting you either with a direct answer or with a resource for an answer. I love digging into the weeds about anything. So questions about courses, about technology, about learning standards and what we cover, that's something I am more than willing to have a conversation with any of you or your colleagues about. You can also find NextWave STEM on all major social media. That is Twitter, it's LinkedIn, it's Instagram, and it's also Facebook. We're not on TikTok, but we do have an intern finally, so we might end up on TikTok. We'll be sure to let you know if NextWave STEM is on TikTok as well. And while I have you here, I want to encourage each of you to sign up or let your colleagues know about next week's webinar as we explore history through augmented reality. This is going to be a really cool topic. Thinking about augmented reality, AR, things like being able to use headsets and even look through the camera lens through your phones and other smart devices to explore the natural world and the human world, the constructed world around us in some new and amazing ways. That is next Tuesday, July 20th, 2021, 4 o'clock Central Time. That will be 5 o'clock Eastern Time. come on out and join us. It's going to be a great, great time. You can register for your spot at nextwavestem.com/STEM training professional development. For each of you all who's taken just a little bit of time out of your day to join us, we are so thankful for you. We appreciate you and your attention, and we appreciate your passion for STEM learning and emerging technology learning with your students. We're hoping that each of you continues to be well, that you find joy throughout the summer as we move closer and closer to the fall. Until we see you next week, everyone be safe, and we'll be talking with you soon. Bye-bye.